Hello everyone, my name is Sebastien Marq from CNES, and I would like to present to you my poster on vicarious calibration of thermal infrared sensors over the ocean and how we would like to use this method for the future TRISHNA mission. I'd like to take a minute just to acknowledge my co-authors, both from CNES and CS Group, both of which are located in Toulouse, France. So here I just put the abstract of my talk just to present to you the context. On the TRISHNA mission, there will be two different instruments, one in the thermal infrared and one visible shortwave infrared. And of course, both of them will be extensively calibrated and characterized in on-ground facilities. However, when we launch an instrument into space, the launch and several years of the mission might affect the quality of the calibration. That's why we want to perform some validation of the calibration in order to make sure that the data remains high quality during the overall life of the mission. For the TIR instrument, we are lucky because we have an onboard calibration device, which is a black body, along with a cold space viewing. However, in order to make sure that this calibration device still works throughout the life of the mission, as it should, we need some other methods. So we are thinking of several vicarious calibration methods, but the one I'd like to focus on today is the calibration method over the ocean. So it relies on meteorological data, which we take from the SMWF, and these data are used to derive both sea surface temperature and the relevant atmospheric variables in order to simulate through radiative transfer the top of atmosphere radiance, which should be observed by the sensor. And we compare that with the measurement of the sensor, then we can assess its calibration. So the TRISHNA mission hasn't been launched yet, but we had the opportunity to test this method over Sentinel-3 SLS-TR data, and so that's what I will be presenting today. Here is a schematic of the principle of the method. So we get the sea surface emissivity from a spectral library, so Aster or EcoStress, and we also have the opportunity to use the formula by Niklos et al. 2009 in order to take into account the variability of the sea surface emissivity with respect to wind speed and zenith viewing angle. As I mentioned earlier, the sea surface temperature comes from ECMWF ERA 5 data. And from ECMWF, we also get gas pressure and temperature profiles, which we can use into radiative transfer codes such as Modtran or RTTOV in order to simulate the TOA hyperspectral radiance. If we convolve this hyperspectral radiance with the sensor bands, then we can get the TOA simulated radiance in the sensor bands. And that we can directly compare to the satellite TOA radiance and then assess the calibration. Here is a small slide to present some very basic elements for the two different missions. So first to talk about the TRISHNA mission. So it will be launched in 2026. It's a CNES ISRO joint mission, and there will be two instruments, one in visible and shortwave infrared and one TIR. The primary mission objectives are terrestrial ecosystem water stress and water use, and also coastal and inland water. You can see here the instrument spectral response function for the TIR instrument. So you can see there are 4 spectral bands between 8 and 12 microns. And now I'm focusing on Sentinel-3 SLS-TR instrument. So there are 2 satellites for Sentinel-3, so 3A and 3B. And SLS-TR has a range of visible and TIR spectral bands, but I will focus here on the band in the thermal infrared. So 3.7 micron, band 7, which is mid-infrared, and then band 8 and 9, which are fully within the thermal infrared range and which are quite similar to TRISHNA TIR3 and TIR4 spectral bands. So that's why we're using this sensor. And here is a schematic of what the acquisition principle is for SLS-TR. So there are 2 different views, which we'll be separating later in the poster. So the first one is the nadir viewing. So it's a regular viewing. It's actually not really nadir. It just means that the along track angle is almost close to 0. So it's viewing nadir in this direction only, but then it spans a swath of about 1400 kilometers, so it's quite large, up to 55 degrees. And then there is another view, which is called the oblique view, which is looking backwards, actually, which has a 55-degree along track angle, and then there is a small across track variation around this position. Here is some elements about the dataset that we use. So we had the opportunity actually to use the data for SLSTR because CNES participates in the calval of the visible and SWIR short validation of the calibration. And so there are some extraction that are being done by the S3 eTrack software, which is operated by the Acri ST company. And we actually get the data for the visible and SWIR spectral bands, but we have the opportunity that the SLSTR TIR band are also extracted. So that's what we are getting some data already extracted and filtered through cloud coverage, for example, or any artifacts. And for 6 different regions over the oceans. So you can see there are 2 in the Pacific, 2 in the Atlantic, 1 in the Indian Ocean, and actually there were 3 in the Pacific. And you here have the statistics of all the acquisition for Sentinel-3 that we have. So overall, we have about 1,600 acquisition, and they're separated. So the ones which we call on Rayleigh scattering calibration side, so they are these zones, but when there is no sun glint, and then the sun glint ones, which are exactly the same zones, but only in sun glint configuration. As I mentioned earlier, meteorological data comes from ECABLE2F ERA 5, so reanalysis data. For radiative transfer, we use RTTOV. And for sea surface emissivity, we use the EcoStress spectral library and the Nicholas et al. Formulation, which depends on zenith viewing angle and wind speed. And here you have a small sketch of the variation of emissivity for different wind speeds as a function of zenith angle. Here are the results that we get, so I will not go in detail through the table. So we are plotting the results as difference of TOA brightness temperature between what is being measured by SLSTR and what is simulated by our software. And what we can say about those results are that there is an excellent consistency within 0 to 0.3 degrees with the SLSTR calibration, so it's very good news. And we can also see the variability of the result is quite small, so the standard deviation are always less than 0.5 degrees, which is a good thing for this method. We can also say that there is no significant bias between Sentinel-3A and Sentinel-3B. And so we plotted those results, but they are not shown on the poster. There is no significant dependence on the result to the location of the oceanic site, water vapor content, wind speed, or solar zenith angle. Just a quick comment about band S7 and 3.7 micron. So in sun-glint viewing, we cannot use the method because the reflective signal in the specular area is quite strong and we don't simulate it. So the results don't mean anything in this region. And just so basically everything goes well, but the minor thing that we can say that we still need to explain is that so first we are not showing it, but the fact that we are taking into account the dependency of the emissivity with respect to viewing angle helps limit the difference between nadir and oblique views. So if we use only one EcoStress emissivity, which is valid for all zenith angle, we get a bias of 0.1 to 0.4 degrees between the nadir and the oblique views. And if we use the formula, which takes into account the dependency with respect to viewing angle, then this difference becomes smaller. So from 0.05 to 0.2 degrees. So much better. It makes sense to take it into account in our simulation. And then we can still see a minor dependency on the zenith viewing angle. You can see that here the difference in brightness temperature actually increases with the zenith viewing angle for this spectral band. So it's S8 for Sentinel-3A. But still, it doesn't explain why there is a difference between the nadir and oblique view, because here we can say that the brightness temperature difference increases with the zenith viewing angle. The oblique viewing has a zenith angle of about 55, so it should be higher than the nadir viewing, but it's not what we see here in the statistics. So there is something still need to be explained about this difference. Another thing that we can see when we plot the data is that there is a very minor dependency to the image brightness temperature. So it might be showing some non-linearity for the sensor, but as the distribution of the data is very limited, so most images have brightness temperatures within 291 to 295 Kelvin, then maybe it's just an artifact of this distribution. So what we'd like to do to advance on that topic is to acquire other acquisitions at different temperatures, so maybe on cold oceans, in order to confirm or refute this behavior. But however, to conclude on this study, we still think that there are some minor aspects to study, but still this method is very promising for the future validation of TRISHNA level 1 products.